Assalamu alaikum friends, myself Humayun Malik, and today we are going to discuss and derive the relation of threshold energy. But before threshold energy, let's discuss what we have already done. We have generally two types of reaction, one in which energy is released and the other in which energy is absorbed. These are exoergic reaction and the other is endoergic reaction. In exoergic reaction, energy is released, and in this case we have Q value positive. By mean of Q value positive, we simply have two conditions. First is that the kinetic energy of product must be greater than the kinetic energy of reactant, and the other is that the total mass of reactant must be greater than the total mass of product. And the other reaction is the endoergic reaction. In endoergic reaction, energy is absorbed, and in this case we have Q value negative, which is the opposite of the exoergic reaction. And by mean of Q value negative, we again have two conditions. First is that the kinetic energy of product must be less than the kinetic energy of reactant, and the other is that the total mass of reactant must be less than the total mass of product. So we get the value of Q value negative. So these are our exoergic reaction and endoergic reaction. So now let's discuss what is meant by threshold energy of a nuclear reaction. It simply means that the amount of energy required to induce an endoergic reaction is called threshold energy. As we have discussed that in endoergic reaction we have to apply the energy to the reaction to perform the reaction, or in other words we can say that in endoergic reaction energy is absorbed, which is the Q value which we have to apply to our projectile particle to perform the endoergic reaction. So the general reaction of the endoergic reaction is written in front of you, which is A plus capital X plus capital Q, which gives us Y plus B, where small a is the projectile particle, capital X is the target nucleus which is stable and initially at rest, and Q is the amount of energy which we have to apply to perform the reaction. And as a result we get the residual nucleus which is denoted by capital Y, and emitted particle which is represented by small b. So this is the general relation of the endoergic reaction, where Q is the amount of energy which is absorbed to perform an endoergic reaction. So now we are going to derive the relation of the threshold energy, but before let's suppose few things. Let we have mc and vc be the mass and velocity of compound nucleus, and ma and vb is the mass and velocity of projectile particle. Then by law of conservation of linear momentum, we know that the linear momentum before collision must be equal to the linear momentum after collision. Linear momentum before collision adds two terms. First is the momentum of the projectile particle and the other is the momentum of the target nucleus, which gives us the momentum of the compound nucleus. But as we know that the velocity of the target nucleus is zero because target nucleus is initially at rest. So by mean of velocity is equal to zero, from the relation P is equal to mv, we have momentum of the target nucleus also zero. So we simply get the momentum of the projectile particle is equal to the momentum of the compound nucleus, from which we get the value of Vc, which is Vc is equal to ma Va divided by mc, and we name this equation as equation 1. And by the definition of threshold energy, we know that we have to apply some amount of energy, which is the Q value, to perform a reaction. So we simply mean that the threshold energy is equal to the kinetic energy of the projectile particle plus the Q, which is the amount of energy which we have to apply, which is equal to the kinetic energy of the compound nucleus, and we name this equation as equation 2. By comparing these equations we get the value of Q, which is equal to the kinetic energy of the compound nucleus minus kinetic energy of the projectile particle, and we name this equation as equation 3. Now we use equation 1 and equation 3 and we simply get the value Q is equal to 1 divided by 2 ma square into Va square divided by mc minus 1 divided by 2 ma Va square. And by taking 1 by 2 ma va square common from two terms, we get 1 by 2 ma va square into ma divided by mc minus 1. By simply taking LCM, we get 1 by 2 ma va square into ma minus mc divided by mc, where mc is the mass of the compound nucleus and ma is the mass of the projectile particle. And as we know that the mass of the compound nucleus is sum of the mass of projectile particle and target nucleus. So we can say that mc is equal to ma plus mx. By simply putting this value in above relation, we get q is equal to 1 divided by 2 ma va square into minus mx divided by mc. Again, putting the value of mc in the above relation, we get minus q is equal to 1 by 2 ma va square into mx divided by mx plus ma. And by the relation of the threshold energy, we simply put the value of kinetic energy of projectile particle is equal to the threshold energy, and as a result we get the final relation, which is required relation of the threshold energy, and it is ETH is equal to minus q into mx plus ma divided by mx. So this was our lecture in which we have calculated the relation and discussed threshold energy. Thank you very much, guys.